Assalamu alaikum. In this video tutorial, you will learn the heat conduction using ANSYS steady state thermal as well as fluent. The problem is taken from this paper. You can find the paper link in the video description. Let's start the ANSYS workbench. To the left side of the workbench window, you can find different analysis systems available in the ANSYS. Now click and drag out the ANSYS steady state thermal and fluent analysis systems to the main project scheme area. Let's start with the steady state thermal module. The first step is to set up the material. The only property needed for the steady state simulation is the material's conductivity, which is given as 1000 watt per meter per Kelvin in the paper. Now close this engineering data tab. The next step is the geometry modeling. Right click and click on the new SpaceClim geometry. Now go to the new sketching plane and select XY plane and make it a plane view. Select a line command and draw a 1 meter vertical line from the origin to the upside, 1 meter to the right, and 1 meter vertical downside. Point 0.15 meter horizontal to the left, 0.5 meter vertical up, 0.1 meter horizontal to left, 0.5 meter vertical down. Now 0.2 meter horizontal to the left, 0.4 meter vertical up, again 0.1 meter horizontal to the left, 0.4 meter vertical down back, 0.2 meter horizontal to the left again, 0.3 meter vertical up, 0.1 meter horizontal to the left, 0.3 meter vertical down again, and close the path. Now switch to 3D mode. Hit the select button and come to the groups tab portion. Select the top edge and click create NS and name it top. Similarly, select the left edge and name it left. Right edge and name it right. Now click and drag to select all the bottom edges and name it bottom. At last, select the surface and name it surface. That's it in the geometry modeling. Now close the SpaceClim window. By keep selecting the geometry cell, change the analysis type to 2D. Now right click the model and edit. It brings up the steady state thermal window. The first step in the window is to select the mesh, and in mesh details Select the element size of 1 centimeter and click Generate. Now the mesh is generated. Expand the named selection portion and you can see all the named boundaries created in the space claim. Select the steady state thermal in the tree. Here you can see different types of the boundary conditions available in ANSYS steady state thermal. In our problem, the only type of boundary condition is temperature. Click on the temperature boundary condition 4 times. Now select the temperature boundary. Select the right edge, click on the geometry and hit apply and apply the temperature magnitude of 300 degrees Celsius. Similarly, select the next temperature boundary condition for the left edge and provide a temperature of 400 degrees Celsius. Select the next temperature boundary condition for the top edge and provide a temperature of 500 degrees Celsius. Now in the named selection, select the bottom named selection and right click, select item in group. Now all the bottom edges selected. Select the next temperature boundary condition and provide a temperature value of 200 degrees Celsius. Now our problem is fully set up. Select the solution portion in the tree and select thermal, temperature results and solve the problem. Now the problem is solved. Select the edge, no wireframe to see the contour bands. Here we can increase the number of bands in our contour plot. To view the temperature at a particular position, select the coordinate system and create a new coordinate system. In the defined by portion, select the global coordinates. Provide the position where you want to measure the temperature value. Change the unit system to meter. In this case, the X value is 0.955 meter and the Y value is 0.825 meter. Come to the solution portion and select probe temperature. In the location method, select the coordinate system and in location, select the new coordinate system that was created. To view the value, right-click the temperature probe and click Evaluate all results. Here you can see the temperature value of 332.78 degrees Celsius. Similarly, we can measure the temperature value at any location by just changing the coordinate system position and re-evaluating the temperature probe. That's it in the steady state thermal. Now close it. Now for the fluent simulation, the geometric and mesh are same. So Grab the model cell from the steady state and transfer it to the setup cell in the Fluent. Right click in the model cell and update. Here you can see the progress. Now right click and edit the Fluent setup. I am selecting the 2 cores out of my 6 core CPU. I also have one dedicated GPU in my system. After that, click Start. Brings up the Fluent window. Here we can check our mesh. The first thing is to change the units from Kelvin to Celsius for temperature. Now moves to the physics tab, turn on the energy model, and it is the only equation needed to solve our conduction problem in the viscous model, as there is no fluid flow, so it will doesn't involve in this simulation. The next step is to define the material within Fluent. Click on materials and change it to the solid. The default material is aluminum. The only property that needs to be modified is thermal conductivity, which is 1000 watt per meter per Kelvin given in the paper. Click change and close. The next step is to apply the material to the domain. Click cell zones, select surface. The material type is already solid. Click edit. It already has aluminum material applied. Click OK. The next step is to apply the boundary conditions. Click boundaries, select the bottom boundary. The boundary type is already a wall. Click edit. Here we have different type of thermal boundary conditions. Like mixed, radiation. In this case, temperature is the only required boundary type. Select the temperature and provide a temperature of 200 degrees Celsius and click OK. Similarly, select the right boundary and edit. Select the boundary type as temperature and provide a temperature value of 300 degrees Celsius and click OK. Select the left boundary and edit. Select the boundary type as temperature and provide a temperature value of 400 degrees Celsius and click OK. At last, select the top boundary and edit. Select the boundary type as temperature and provide a temperature value of 500 degrees Celsius and click OK. Now boundaries are defined. Move to the Solution tab. Select the Solution method. Change the coupling scheme to simple. And discretization scheme to second order. In the initialization method, hybrid is already selected. Click Initialize. In calculation, click Run Calculation. Provide the just 50 number of iterations and click Calculate. Just in 5 iterations, the energy equation is converged. This is it in the Fluent. Close the application. Right click the results cell and edit. Click the insert contour, keep the same name and click OK. In the location, select symmetry 1 or symmetry 2. Select the variable temperature and hit apply. To change the legend view, double click default legend view 1. In details, go to the appearance tab and change the precision type to fixed. Come back to contour 1 and change the number of contours to 20. The same way, we change the number of contours to any number like 50. To view the temperature at a particular position, go to the location point, keep the same name and click OK. Provide the position. In this case, the X value is 0.955, the Y value is 0.825 and the Z value is 0. Click apply. The point is not visible, so let's change its properties. In the color tab, change the color to black, and in the symbol tab, change the symbol type to ball and size to 0.5. To measure the temperature, go to the calculators tab and select the function calculator here. In the function list, go down and select probe. In location, select point 1 and variable as temperature. Also, click on show equivalent expression and hit calculate. In the results area, select and copy the expression. Now come to the expression tab and calculate a new expression. Right click and click new and named it temp. In the definition area, press Ctrl V to paste the expression. Add minus 273.15 Kelvin in the expression to change the temperature value to Celsius. One thing keeps in mind that the units are case sensitive and you should provide capital K here. Now hit apply. The resulting temperature value of 332.244 is in degree Celsius. Similarly, we can measure the temperature value at any location by just changing the X and Y position and re-evaluating the temp expression. Let's evaluate for another point. Change the x value to 0.055, the y value to 0.135 and click apply. Here in the viewer, you can see the point is shifted to a new location. Go to the expression tab and just hit apply. Here you have a new temperature value of 320.109 degrees Celsius. This is it in the CFD post. Now close it and save your project. Here is the resulting temperature table. You can see the temperature values at different locations from the paper, steady state thermal and fluent. The difference in the temperature values is negligible. This is it for this tutorial. Thanks for watching. If you like this effort, please hit the like button and subscribe to the channel.